Okay, so this is the second lecture in this series on free energy and spontaneity. This is where we're going to take our enthalpy and our entropy and put it together to determine whether a reaction really will be spontaneous or not. Because we can often use enthalpy to do that, but not always. So here's the third thing we're looking at is free energy, which is given by delta G. It's called Gibbs free energy, which is where we get G. And the free energy is the total energy that could be released by a product potentially. And so what we find is that delta G is negative, then a process will be spontaneous, theoretically. And if delta G is positive, then the process will be non-spontaneous. Or in other words, if delta G is negative, then it's a downhill process to get from here to there. But if delta G is positive, then it would be like an uphill process to get from here to there. It's not, balls don't roll uphill, they only roll downhill. Does that make sense? Kinda. The delta G is negative, we're going to call this exergonic. And delta G is positive, we're going to call it endergonic. And we can even, it looks kind of like a ball rolling, but we'll often have these we call these an energy diagram to kind of explain what's going on. And we could say, this is my reaction coordinates. So as my reaction proceeds, and then the y-axis is my relative energy level. So if I start at a high energy level for my reactant, and I end at a low energy level for my product, that would be spontaneous, because that would be a downhill process. That would be like the ball rolling downhill. My delta G is negative because my products have less energy than my reactants. So that energy must have been released. Whereas if I do this and I find that my products are lower in energy than my reactants are lower in energy than my products, then when I draw this little thing, we'll find, okay, I had to gain energy to get from here to there. So my overall free energy is positive. It's not spontaneous for balls to roll uphill. You guys can all hear me, hopefully. Anybody else having problems with connection and sound? Diana, try exiting and reconnecting and see if that helps. Try that. So then on the left-hand side is energy diagram for a reaction which is spontaneous. On the right-hand side, one that's not spontaneous. Okay. Now, there's a little bit more to it than that. Everything that is spontaneous, every reaction that is spontaneous or process, doesn't necessarily happen spontaneously in the way that we like to think of the word spontaneous in the English language. In the English language, we're going to say if it's spontaneous, then it's like already happened. It's just, it happens all by itself with nothing on the outside. But for chemistry, for delta G, when we say it's spontaneous, we're just saying that my reactants are higher in energy than my products. So that if I could find a way to get from here to there, I would definitely do it. But that doesn't mean there's always a way, okay? It's a little bit of a hump here. And for some reactions, it's a bigger hump than other reactions. Let me draw it here. Give you an example. My reactants here, my products here, that would be a spontaneous reaction. But sometimes the path to get from here to there, I have to go uphill first. The difference between the energy levels is known as your change in energy, which we were just talking about. But the difference between where I start and how high I have to go to get over that hump, that difference is known as the energy of activation. The amount of energy it takes to get that ball rolling in the first place, okay? Now, this will make perfect sense to you guys as we all live in Utah, which is very high elevation. And everybody knows that water flows downhill, right? I hope you guys know that. Do you guys know that water likes to flow downhill? Normally likes to do that. If you have water at high elevation, it should. So theoretically, it would be absolutely favorable for the Great Salt Lake at this high elevation to drain into the ocean because it's a much lower elevation. That is a favorable process. Water flows downhill, right? Why doesn't the Great Salt Lake just spontaneously drain into the ocean? But overall, it's downhill, right? You guys are exactly correct. You're exactly correct. There's no route to take the Great Salt Lake down to the ocean. If we dug a tunnel, we could create a route and we could drain it. That could work. We probably wouldn't want to do that, but that would cause it to drain, would it not? But absent our creating an artificial route, it can't get over the mountains to drain into the ocean. Okay, so there's no path, no way to get there because it's not going to flow uphill over the mountains. Okay, so if we have a really high activation energy, then that might mean that even though it's spontaneous, it doesn't happen, or maybe it happens really slowly. Okay, so the delta G is going to tell us whether it's spontaneous. Energy of activation is going to tell us if it's possible, or another way of looking at it is to tell us the rate at which it occurs. Okay, if the energy of activation is small, that gives us a fast reaction because it's really easy to get over that little hump. If my energy of activation is large, like this big mountain here, then that's going to give us a really slow reaction. Okay. Good example of some processes here. For instance, gasoline has stored potential energy. And that is because gasoline is a high energy molecule, and when it burns, it's going to release a lot of heat and energy. And so we know this is a spontaneous process, but we're glad that it doesn't just happen all by itself because we like to ship it and store it and put it in our cars and then activate it when we need it. So what would it take to activate gasoline to burn? Just a little spark, just a little flame. You don't need to actively be adding flame to it to get it to burn. You just add one spark. Here we go. This is gasoline because it's exothermic and it has a very small activation energy. You just add a little spark and it just keeps going forever until it's all burned up. Perfect. A good example of something which would be favorable but doesn't happen is diamonds actually are much higher in energy than coal. So diamonds should spontaneously decompose into coal, but they don't have a path. There's no easy way for those chemical bonds to shift, so the energy of activation for that process is too high. So even though it would be spontaneous for diamonds to decompose into coal, it's not something that happens because the energy of activation is so high that the rate is essentially zero. You guys following me a little bit here? What it means to be spontaneous and how that energy of activation plays into that? Sorta. Okay. We'll talk about one more thing and then we're gonna do some, well, actually, hang on a second. Let's go over here. So here we go. Section 3 is looking just at delta G. So write a chemical reaction for any of the processes that are given, and then you tell me whether essentially it's spontaneous. And here's how I define spontaneous. If it continues without any external assistance after it's begun. In other words, I give it that teeny bit of activation energy and then it just does it all itself. So dissolving sugar in water. Some of these, actually all of these, I'm expecting you guys to use a little bit of your common sense. If I take water and I add it to sugar, C12H22O11, aqueous. Is that spontaneous? Will sugar dissolve in water? DB, diamonds-into-coal is such a slow reaction that the rate is essentially zero. We can say it just doesn't happen. Caleb is exactly right. This is spontaneous because sugar does dissolve in water. You guys should know this is kind of the level of common sense I expect you to bring to an exam. You guys should know that sugar dissolves in water. Okay, automobile gasoline evaporating on a hot day. So you spill some gas on the pavement. It's a hot day. This was a liquid and it becomes a gas. Do you have to intervene or does that just happen? You don't. You don't know by looking at the equation. You know because of common sense. Caleb. So you guys have more common sense than you think you do. You guys, almost all of you guys have driven a car, I'm sure. And if you've driven a car, then I'm assuming that almost all of you guys have actually put gas into that car. So you guys know something about the properties of gasoline. Gasoline will evaporate on its own and quickly. That's spontaneous. Excellent. Okay. Burning propane gas. So burning is another word for combustion. You guys know how to write a combustion reaction. A fuel consumes oxygen, forms carbon dioxide and water. We don't need to balance it. I want you guys to tell me, does propane gas burn on its own once you get it started? Yeah, no intervention required. You just have to give it a spark and it goes for forever. Okay, so delta G is negative, that's spontaneous. Finally, water from the air condensing on the side of a cold glass. So that would be this one up here. Gas goes to form a liquid. You probably did, Megan, but you didn't think about it in those terms. Because you guys, anytime you go to fill up your car, you can smell the gasoline, right? You guys have smelled gasoline at a gas station. You can't smell it unless it has become a gas airborne so it can enter your nose. Because you're obviously not like snorting liquid gasoline at the gas station to make yourself smell it. But if you can smell it, then there's gas particles there. By the way, don't go snort liquid gasoline. You can smell coffee. What you're smelling are scent molecules, organic molecules that have entered the gas phase, yes. Some liquids will decompose if they get hot enough to start evaporating. I could come up with one, but on the top of my head, I'm thinking that most of them would evaporate. Okay, guys. Will water condense on the side of a cold glass like here? All by itself? Do you have to help it? All by itself. So all of these, I should have put something non-spontaneous here. Let's see, what would be an example of a non-spontaneous process? Your cell phone gains a charge overnight without being plugged in. Would that be spontaneous? It wouldn't be it won't happen. It's not spontaneous because charging the battery is a non-spontaneous process. That's why you have to plug it into the wall and constantly feed it energy to get the battery to be charged. So it looks like there's no external assistance, but that's because you aren't doing that active energy. It's your house's energy output that's doing that active pumping energy into it. Okay. Now what we need to do is talk about the relationship between our change of free energy and our enthalpy and our entropy, how those kind of come together. And there's an equation that we use, an equation that I will give you on the test, an equation you will not have to do math with, but you will have to perform logic puzzles with. Yay, no math, but logic puzzles are almost a little bit harder. If I give you the math, you just plug it in, like plug and chug, right? But logic puzzles sometimes are a little bit more daunting, okay? So I don't know if it's better or worse, but this is what we get. So my free energy is equal to, the value of my free energy is equal to the value of my enthalpy minus the temperature, and this is a temperature in Kelvin. So this value is always a positive value because the Kelvin temperature scale goes from 0 to infinity, but it never is negative because 0 is absolute 0, okay? Multiplied, so the temperature in Kelvin then is multiplied by the change in entropy, okay? And we know something about whether delta H is positive or negative. We can know something about whether delta S is positive or negative. We could use that to kind of do some little mental math to determine whether delta G would be positive or negative, and vice versa, okay? So let's go through, let's see, let's make some predictions. So the equation here is our free energy is equal to our enthalpy minus the temperature in Kelvin multiplied by our entropy, right? Delta H is enthalpy, delta S is entropy, delta G is our free energy. Okay, so for instance, I'm going to put a little chart here. Let's see. And then we'll see if we can fill in what we know about delta H, delta S, and delta G. Okay, so if delta H is positive and delta S is negative, I would have a positive value subtracting, this is going to be a positive times a negative. What's a positive times a negative? A negative. And what happens when I subtract a negative? What does that become? Becomes positive. So if I have a positive delta H and a negative delta S, I end up with a positive plus another value. If I have a positive and I add another value, the sign of delta G in that case can only be positive. I hope you guys see that. Like if I have positive 10 and I add some more, it's never going to be a negative number. You guys following me there? This is my logic puzzle. Let's try it this way. If delta H is negative and delta S is positive, so here I would have a negative value and I would be subtracting two positives multiplied together. So a positive times a positive is a positive. So a negative value minus another value. Delta G then would always have to be negative because I have a negative value that's becoming more negative. Like negative 10 minus 5. It's going to become more negative. Are you guys tentatively following me so far? Not following me at all? It's kind of a tentative. If you are curious, you could always plug values in, okay? Plug in a few different values to make sure that you're getting it right. Let's say, for instance, delta H was positive 10. So in this case, like delta H, positive 10, and delta S was negative 10. And let's just say K is always 10, okay? So if I've got 10 minus a 10 times a negative 10. Now you guys told me positive times a negative is a negative. That would give me negative 100. So minus a negative 100 is going to become positive 100. So then I'd have 10 plus 100. I'm becoming more positive. So my delta G is going to have to be positive. Okay, this is my logic puzzle. Again, if delta H is negative, I start with a negative value and I subtract a positive times a positive, delta S is positive. Positive times a positive is positive. So if I'm subtracting a positive, I'm becoming more negative. So I start out negative and I become more negative as I subtract T delta S. Delta G then must be negative by definition, just by the way that relationship stands. Let's try if I have two negatives. This is where it starts to get dodgy. If I start with a negative, and here I'm subtracting a positive times a negative, and you guys told me a positive times a negative, if this is negative, positive times a negative gives me a negative. Subtracting a negative gives me a positive contribution. So then I'd have then a negative delta H, and then I'm adding a positive contribution from the T delta S. Now my delta G will depend on my temperature, because if I'm at a high temperature, then this piece of the puzzle is stronger, so it would be positive. But if I'm at a really low temperature, then it doesn't matter how big delta S is, and then the delta H part of the contribution would be more important. So here then we find that we'll be negative at low temperatures and positive at high temperatures. Now, what is a low temperature? What is a high temperature? That depends entirely on the specific process we're talking about. But we do find that this is a temperature specific process to determining whether my process is spontaneous or not. Some processes are spontaneous at low temperatures and not at high temperatures, and vice versa. So let's do this last one here. Positive delta H, positive delta S. Positive delta H would go here. Positive delta S times the positive temperature gives me a positive value here. Minus a positive is going to turn this into a negative contribution overall. So again, we find it depends on temperature. If I have a very high temperature, then subtracting that positive value is a bigger deal. So I would become negative at a high temperature, or spontaneous at a high temperature. If I was at a very low temperature, then this wouldn't make as big a difference, and I would rely more on delta H, which then would be positive. Positive at a low temperature. I know you guys have all gone through the algebra to know that a positive times a positive is a positive. Positive times a negative is a negative. Subtracting a negative would make that positive. That's essentially all we're doing here. Okay, so what I want to do then is to take this chart, and you don't have to memorize it if you can deduce it by following these rules here, and apply it to what we can see in this in-class activity sheet here for 17.1, or 7.1, pardon. In some of these, you're going to know something about delta H and delta S. You can predict something about delta G. For some, you'll know something about delta G and delta S, and you can predict something about delta H. For some of these, you can know something about delta H and delta G, which would hopefully help you predict something for delta S. So let's do just a few of these, and I hope that this will kind of help us all gel in your mind. I know that at the beginning it's going to feel a little bit confusing, but we can do this. Okay, so delta G is delta H minus the temperature in Kelvin times delta S. And again, we're not going to be plugging in any numbers. I'm not going to be doing math. That's just a logic puzzle. Okay. Some of these you can look at the reaction. You can assign all the values. Let's try this one right here. Combustion of ethanol. I'm burning ethanol. It's already balanced. You guys can tell me, do I know anything about heat for this process? Would burning ethanol release heat, or would it absorb heat? definitely releases heat. So the delta H is negative because it's exothermic, it releases heat. Okay. Delta S for this reaction, can we look at this? Can we make any predictions about the change in entropy based on what that reaction looks like? Definitely going towards more disorder. I have 4 molecules on the left, 5 on the right. Okay. Now, without having to go through the mental logic puzzle here, do we know anything about ethanol? Is it spontaneous? Does it burn with just a spark? It's definitely going to burn. Definitely spontaneous. So this one we didn't even have to go through the whole logic puzzle. But if we did, we would say delta H is negative, delta S is positive. I'm essentially subtracting a positive, so I'm becoming more negative. So I started out negative, I'm becoming more negative. So delta G is definitely, according to the laws of the universe, it has to be spontaneous based on what we know about delta H and delta S. H2O in this case is a gas because when you burn something, there's enough heat produced that it vaporizes the water, which is why when you burn something, you don't get a puddle of water right there as you're burning it. Good question though, because water is always formed, but because of the heat, it always ends up a gas. Okay, let's look at iron resting. We'll assign the ones we do know and then see if we can deduce the ones we don't. Okay, so iron resting, here's the process. I don't think we know anything about the change in heat for iron resting. Like it's a slow enough process that if it does release or absorb heat, we can't really feel that happening. So let's skip on to delta S. Can we say anything about delta S for this process? Hang on a second. We could say something about delta S. I've got 4 iron atoms combining with 3 oxygen molecules to make 2 iron oxide molecules. Furthermore, all of these are gases and I'm going to form a solid. It's the same things we were looking for in this section here, right? For predicting delta S. So it's negative. I'm definitely going to form more order here. Order, so negative. Perfect. Okay, can we predict anything about delta G? Does iron spontaneously rust at, by the way, this is a very warm day. So conditions that you and I would be familiar with. Jay Houston says yes. You guys agree? Does iron just rust? Like if I stuck a car out in my front lawn and left it there for 10 years, would it be pretty rusty after 10 years? Assuming it was actually made with iron and not just aluminum. Yeah, so this is a spontaneous process. So we know something about this process. It is spontaneous. Okay, let's see if we can use these two things, one that we knew from common sense, one we were able to predict by looking at the reaction, to predict something about delta H. Okay, we know that delta G is negative, and we know that delta S is negative. Remember, that temperature is always positive. So I have a positive times a negative. Positive times a negative is a negative. And I'm subtracting a negative, which means that this whole piece, as I subtract a negative, that's going to make this whole piece positive. Did everybody follow me there? If you didn't follow, say something. So at least I know that you guys can hear me. Okay, so we knew that delta S was negative, but when I plugged it into the T delta S, a positive times a negative becomes negative. Subtracting a negative would make this a positive contribution. Well, we know that this is spontaneous. We know that this is negative. So if this is making things more positive, then my delta H has to be what in order to make this equal a negative value? Has to be negative. Since my net result is negative, and this is a positive contributor, this basically has to cancel that out and say, nope, I've got to make it more negative because my delta G is negative. So we don't ever see it on the time scale that it happens, but apparently making iron oxide from iron and oxygen is a exothermic process. We can determine from this little logic puzzle here. Okay, let's try this guy. Solid water to liquid water at 5 degrees Celsius. Going from a solid to a liquid, do we know anything about delta H going from a solid to a liquid? Hang on, let's see, up here. We determined that solids had less movement energy than liquids. So going from a solid to a liquid is going to give me a positive delta H, right? Because I am increasing the heat energy available, increasing my temperature. You guys with me? So that should be positive. So going from a solid to a liquid, so delta H should be positive, according to the rules that we memorized for delta H. And my delta S, according to the rules we memorized for delta S, going from a solid to a liquid, is that more disorder or more order? Disorder. Okay, liquids are more disordered than solids. So again, insofar as is possible for delta H and delta S, we're going to follow these exact same rules that we already laid out about what it means to be positive or negative. Nothing, we're not going to engage in mental gymnastics unless we absolutely have to, okay? So going from a solid to a liquid, that's more disordered because the solid, everything is fixed in its position. The liquid things can move. Okay, so absorbs heat, tends towards more disorder. Now, before we go through the mental gymnastics, let's ask ourselves, does solid water become liquid water spontaneously at 5 degrees Celsius? See, I gave you a temperature here. That's not because I want you to plug that in here. No, it's because I want you to use some common sense. What do we call this process where solid water becomes liquid water? Melting. Yes, okay. So ice melting. Will ice melt at 5 degrees Celsius? Shauna Meredith says yes. Anybody second? Katie says yes. Yes, ice will melt at 5 degrees Celsius. In fact, at what temperature does ice start to melt? Yeah, 0 is freezing. So anything above freezing, it's going to start to melt. So this is spontaneous, and I didn't even have to do mental gymnastics to determine it. If I did mental gymnastics, I would find that I've got a positive minus a positive, so it depends on temperature, and that's where you would say, but I don't have data to plug in. Okay, that's why you're going to use a little bit of common sense. You do have to know, the common sense that you have to know, 0 degrees Celsius is the freezing point or the melting point of water. I do expect you to know that. Excellent. Okay, we're going to do one more, and then we really do need to move on to the next lecture, or the next section. Let's do this one. Dissolving NH4NO3 in water, it makes instant cold packs. So NH4NO3 goes from a solid, but if it's dissolved in water, it becomes aqueous. Okay. Do we know anything about delta H? Change in heat. Would heat be absorbed in this process or released in this process? Jay Houston says absorbed, and he is exactly right. She is. Is that Joyce? She is exactly right. Pardon. How did you know it was positive? I mean, the reaction itself says nothing. Well, it goes from solid to aqueous. So that is, yeah, that is. But the other thing you know is it makes instant cold packs. In other words, it is absorbing the heat from your hands, and that's why your hands get colder, because it's absorbing that heat. So because it makes its surroundings colder, it must be absorbing the heat. So delta H is positive. Okay, delta S, is this more order, more disorder? Definitely more disorder. So this is a positive value because that's more disorder. Okay, is this spontaneous? Dump that in water, will it dissolve? Excellent, yep. Dump that in water, it will dissolve. If it didn't, it wouldn't be very useful as an instant cold pack, would it? Because it wouldn't actually make a cold pack. It would just be like, you wanted me to dissolve, but I'm not good. Okay, I think you guys should practice these and talk about them on the forums or bring them on Wednesday. We can talk about them before we take the test. Okay, the next section here has you draw energy diagrams, and we actually already did this over here, right? We were showing, oops, I'm sorry. This is an exergonic. This would be endergonic. This would be fast because it has a very small energy of activation. This would be slow because it has a very large energy of activation, right? So the difference is, what you're looking at is the difference between my beginning and end point, and the difference between my beginning point and the top of that ridge. So if we do that here they're doing exothermic, so they're looking at it for delta H, but it's essentially the same as delta G. Delta H is usually a pretty good predictor of delta G, but essentially I want to see the same thing. So if it's exothermic, my reactants are higher energy than my products. Slow says my energy of activation is really high. So the difference between my reactants and my little hump is big. So that would be exothermic but slow. Endothermic but fast tells me my products are higher in energy than my reactants. That's what endothermic would mean. And higher in heat energy because it's thermic. Very fast means my energy of activation is relatively small compared to the difference here. So that's a very little hump. Okay. Can you guys see that little hump makes it fast? The big hump makes it slow. And the difference between these two going downhill makes it negative. Going uphill makes it positive. If I gave you an energy diagram on the exam, could you interpret that? Tell me if it was fast or slow or spontaneous or not. Okay. All right. Excellent. All right, the last section here looks like it's something new and different, but it's really not. All I'm doing is applying some information about delta H, so this is heat energy, to what we've already talked about in chapters 5 and 6 about writing and balancing equations and doing dimensional analysis with them. So for instance, part A, this is straight out of chapter 5, write a balanced equation for the combustion reaction. Oh, well, you know what combustion is, C8H18 plus oxygen goes to form CO2 plus water. And I think if we balance it, let's see, we put 8 here and then 9 here. That would give me 16 plus 9 would be 25 but these come in pairs, so I'm going to have to put 25 halves here and then multiply everything by 2. So that then would be 2, 25, 16, and 18. So there we go, balanced equation for the combustion reaction. The sign of, I couldn't put a delta for some reason, delta H for that reaction. I told you it was released. And you know that you're burning something. So what's the sign of delta H? I've got 1 vote for positive, 1 vote for negative. Any tiebreaker votes? Robin votes for negative. It is negative. Delta H is negative because negative is releasing heat. So since it was released, then we know it's negative. Or because essentially in the process, your surroundings are getting hotter because they're absorbing all the heat that was released. That's a clue too. Okay, the rest of this is dimensional analysis. I just told you right here, this is information. You know that 5 grams will give me 239.5 kcals. So I want to know how much for 1 mole. Okay, no big deal. I can convert from moles of C8H18 to grams of C8H18, and then I could use this to convert from grams to kcals. How would I go from moles to grams? Don't tell me you forgot already. I don't need a number, I just need the description of the process. How would you convert from moles to grams? Or if I gave you grams, how would you convert to moles? You use the molar mass, right? I'm just going to add up 12 carbon atoms plus 18 hydrogen atoms, and I'm going to put the molar mass right here. So molar mass will allow me to convert from moles to grams, and then I can plug this in here, and I would put 5 grams of C8H18 on the bottom. It's going to give me 239.5 kcals. My moles will cancel here, my grams will cancel here, and then I'll be left with the energy that's released. So this is how, there's a few questions like this on the Chapter 7 homework, and this is exactly how you're going to do it. And it's just adding in this extra little piece of conversion in a dimensional analysis if I give you this kind of energy. And these are C, D, and E are exactly just variations of what we just did in C. So I'm going to let you guys try those and then bring it to class on Monday. We can talk, or on Wednesday, we could talk about them before you take the exam if you feel like you need to. But it's just dimensional analysis. That's all it is. And whatever I give you, that's what you're going to use. Or on the homework, that's what they give you. All right, and then the energy diagram, you know that it's exothermic. You know that's spontaneous, so your products are lower in energy than your reactants. And you know that all it takes is a spark, so my energy of activation is pretty small. So it's going to be one of these. And that's it